spaceship for a high-speed journey to a distant star and back. For the astronaut, from liftoff to landing takes just 2 hours on the ship's clock. They expect to see their sibling only hours older, but instead, their twin on Earth is now old, having lived through 80 years. This is the twin paradox, a direct consequence of Einstein's special relativity. It reveals a mind-bending truth. Time is not absolute. Your experience of time, the rate your personal clock ticks, depends on how you move through space. For the Earth twin, decades of seasons, news cycles, and life events. For the traveler, just enough time to watch a movie and have a snack. The journeys aren't symmetrical. The astronaut accelerates, turns around, and decelerates. The Earth twin does not. That asymmetry in space-time paths creates the age gap, making one effectively a future time traveler. This isn't just theory. Atomic clocks flown on airplanes and satellites lagged behind ground clocks, just as Einstein predicted. To get 2 hours versus 80 years, you must approach light speed, roughly 99.99999% of c. Yeah. So why does moving fast make your clock run slow? This is the core of time dilation. Einstein taught us to treat space and time as a single fabric, space-time. Everything moves through this four-dimensional fabric. Even sitting still, you hurtle through time. Your total motion through space-time is constant and equals the speed of light. Like a car with one top speed, use it to go north through time or divert some east through space. When you move through space, you divert motion away from the time dimension. The faster you travel through space, the slower your personal clock runs relative to someone stationary. That slowdown affects everything: your heartbeat, atomic decay, all processes. At 99.9% of light speed, almost all motion is through space, so motion through time crawls. For every 80 years on Earth, only hours pass on the ship. The Lorentz factor quantifies this. At everyday speeds, gamma is near 1. As you approach CC, it skyrockets toward infinity. Time dilation becomes extreme, a cosmic speed bump for time itself. Great for crossing distance, bittersweet for humans. You leap into the future of home. Now, a more speculative idea. What if you didn't travel through space at all? Imagine an instant jump. The ship vanishes here and reappears there, light years away. Less like driving across the country, more like changing your GPS coordinates instantly. Crucial difference: velocity. No roaring cruise, practically zero velocity during the jump. At rest at origin, a transition, then at rest at destination. Speculatively, a phase transition of matter shifts position on a deeper, grid-like structure of spacetime. Think of a checker piece. You don't slide across squares. You pick it up and place it on a distant square. Physicists might call this a metric discontinuity, a break in the continuous path through space-time. Your world line pauses at one point and resumes at another, far away. The jump itself adds no time, avoiding the time debt of high-speed travel. No long acceleration means no significant time dilation. Both clocks stay nearly in sync. Not travel in the usual sense, translocation. Let's revisit our twins with this new technology. Mission: visit a planet around Proxima Centauri, about 4 light-years away. The jump drive engages. For a fleeting moment, the ship vanishes. Then reappears in orbit around the distant planet. The astronaut spends 1 hour collecting data, then jumps back. Total ship time: just over 1 hour. How much time passed on Earth? With no relativistic cruise, the twin paradox doesn't apply. Clocks remain in sync. The traveling twin steps out to meet a sibling who has also aged by only about an hour. They share data and plan the next adventure together. The 80-year age gap has vanished. This changes interstellar exploration. No impassable time barrier between generations. Breakfast on Earth, a meeting at Alpha Centauri, and back home for dinner. The galaxy shrinks from vast ocean to a network of connected islands. A common objection to FTL travel is that it violates fundamental physics. As an object with mass nears light speed, its effective mass increases. Reaching light speed would require infinite energy. Impossible. True FTL could break causality, effects before causes. You might arrive before you left, creating paradoxes. The instant jump sidesteps this. The ship never actually exceeds light speed. It barely travels conventionally. Instead, it changes spatial coordinates by a different mechanism. No infinite velocity means no infinite energy. Energy is spent initiating a finite jump or phase shift. This preserves causality. Cause precedes effect. You disappear here and appear there now, not in the past. Both twins agree. The ship left, was gone, then returned. No causal loops. Relativity governs motion through space-time. The jump moves without traversing the in-between space-time. Change the mode of movement. Change the rules. Avoid the penalties of brute forcing past C. If realized, the instant jump would be the most transformative invention in human history. It would alter our relationship with the cosmos. Stars would shift from untouchable points of light to reachable places. The emptiness between systems would no longer be an insurmountable barrier of time and space. Humanity could become truly galactic. Colonies could remain cohesive. Trade, travel, communication, and rapid mutual support. Science would explode forward. Visit worlds we now only study from afar. Sample directly. We could study black holes, neutron stars, and nebulae up close. The pace of discovery would accelerate beyond imagination. But we must be clear, this remains highly speculative, far from engineering reality. It may require a revolution in quantum mechanics, gravity, and the structure of space-time. Its value is a new way to think beyond brute force relativity, a target to aim for. It lets us dream of reaching the stars, together.
In the sunlit agora, Aristotle and his student pause beside a weaver's taut cloth.
Master, stones fall toward us, yet the far heavens seem to drift apart. Imagine there is only cloth. What you call stone or star is cloth tightly gathered. Dense gatherings pull upon looser threads, while broad, even regions slowly relax their strain. So gravity is knots following tension, and expansion is the cloth easing toward balance.
Hello, my name is Rod Kowicki. I'm doing this video on physics, mathematics. I'm developing a new theory on physics. I've done about 15 years of study and everything. A lot of things keeps coming up. Relativity seems to be the accepted theory. When anybody wants to talk about physics, they talk about relativity. Relativity has a lot of flaws, I hate to say. And I'm going to tell you about one in this video. My name is Rod Kowicki. Thank you.
Okay, quick brain stretch. What does relativity actually say about going close to the speed of light? In Einstein's special relativity, as your velocity creeps toward light speed, your energy shoots up like crazy. You've seen the famous line, E equals mc squared. The full picture, E equals gamma times mc squared. Gamma equals 1 over the square root of 1 minus v squared over c squared. As your speed v approaches c, that denominator goes to 0, gamma explodes, and the energy you need blows up. Modern physics doesn't say your mass literally becomes infinite. It says the energy required for more acceleration diverges. Translation: the barrier is energy, not magic infinite mass. Now here's a different lens. My quanta physics interpretation. Instead of energy going to infinity, I'm proposing a new mechanism. The mass energy of matter is fixed by its subatomic blueprint from the Big Bang. When you accelerate, you don't grow infinite mass. You take on dynamic mass loading. Think of it like temporary inertial weight, base inertial state, plus acceleration equals extra load. And that increase might be finite. Say it tops out around 50%, not infinity. In this model, the mass increase depends on acceleration itself, not on velocity sneaking up on C. Push harder, you feel heavier. Ease off, you drop back to normal. Here's the analogy. Earth's gravity gives you 1g on the ground. When a rocket launches and pulls 2g, you feel twice your weight. Thrust must beat gravity's loading. My interpretation extends that intuition to near-light motion. Not go faster, get infinite mass, but accelerate harder, get more inertial weight. A fast spacecraft, even at extreme speed, would mainly feel added load during the push. Let E represent how strongly acceleration couples into that load. More A, more load. Level off, it eases. Here's the core claim. Velocity near light speed doesn't demand infinite energy, because matter's energy is set by its subatomic structure. Acceleration temporarily increases inertial load. Deceleration removes it. The mass returns to baseline. The ceiling becomes an engineering problem, not a fundamental wall. How does this fit my broader quanta physics ideas? Picture layered space field membranes, a structured vacuum, real texture. Instead of warping space-time, a ship pushes through those vacuum fields. The thrusters spend energy on speed, not on making mass. Think about the Higgs field. Virtual particles flicker, ready to confer mass. In my framework, you set up a negative ground between the ship and the vacuum, dialing down resistance. At large standoff, effects like the Casimir pressure, normally tiny, stack in your favor, acting like a negative drag. Pair that with superluminal corridors as engineered routes through the vacuum structure, no space crunching required. So here's the proposition, the Kawecki finite inertial mass theorem. In a universe built from fixed subatomic mass energy structures, the inertial mass of an accelerating body rises as a finite function of acceleration, not to infinity as velocity approaches light speed. Einstein sets the gold standard for what we've measured. This is a bold alternative for what we haven't yet. Materials that can take the G, fields that cut the drag, power systems that keep pushing. No magic infinities, just the hardest engineering we've ever done. Ready to test it?